Okay, welcome back. We're going to finish what we started last time, which is about diffraction. So we talked about the single slit diffraction, right? Here's our result. We found this. The slit has width A. And what you see on the screen is light spreading out. So you will see some bright here. You see some light here, and then it gets dark here. You got a dark spot here and a dark spot here. This is m equal to 1. This is minus 1. And then you see bright, right? And then you see bright, bright. Keep mixing my colors here. You'll see bright. Okay. Okay. And this is m equal to 2. This is minus 2. This is minus 3. This is plus 3, and so on, right? And the condition for the dark spots was A sine theta is equal to m times lambda, and m was plus or minus 1, plus or minus 2, and so on. There were no zeros, right? The zero was not there. Zero is the bright spot. Then we discussed how bright are they? What's the intensity in there? And we found this. Intensity. This is for the diffraction, right? The intensity. The distribution of the intensity was it is I is equal to I naught, and then the sine of beta over 2 divided by beta over 2 squared, which is equal to I naught times the sine of I A over lambda sine of theta over pi A over lambda sine of theta, the whole thing squared. Okay. Meaning beta was equal to 2 pi A over lambda sine of theta. All this we did last time, right? And we said this confirms our the condition for the dark spots, what their location is. Their location is when the intensity is equal to 0, and the intensity is equal to 0. Oh, this slide. The intensity is equal to 0 when the sine is equal to 0, right? And then the sine is equal to 0 if inside the sine is a multiple of pi. And then it confirmed our this condition here, right? And then we said the special case when theta is equal to 0, meaning it's here, the intensity was equal to just I naught, because it was basically the sine of 0 over 0, right? The limit as you approach 0, you get 1. Okay. So we saw that last time. And with that said, I have a couple of examples I would like to do with this. Does anyone have a question on this one or no? No. Okay. So let's do a couple examples. Here's the first one. Example 1. So example one, suppose the intensity in the middle here, the intensity, so suppose I is equal to I naught when theta is equal to 0, right? What is, find I, find I, intensity when beta is equal to 66 radians. What's the intensity if beta is equal to 66 radians? You see beta is equal to 2 pi a over lambda sine theta, and it can be 60, it just depends on what these are, right? 2 pi is what, 6 something, right? 6.28 something radians, and then it can be larger, it can get larger. So I think we would just simply go here, right, and plug in the numbers. Right? So we say, so let's do the solution to this one. We have intensity is equal to I naught times the sine of beta over 2, that's 66 over 2, divided by 66 over 2 squared. 66 over 2 is obviously 33. Plug in the numbers. If you'd like a moment to plug them in, or you want me to just tell you the answer? Maybe it's not very illuminating to do much with this one. I'll just write it. It's 9.2 times 10 to the minus 4 I naught. Okay? That's it. In terms of I naught. So let's make this part A, part B. If theta is 7 degrees at this point, if at this point when beta is 66, theta is actually is 7 degrees. Yeah, 7 degrees. How many multiples of lambda is A? How many multiples of lambda is A? By the way, in here, yeah, maybe I should have let you plug it in. Now I think about it. When you put sine of 66 over 2, what mode should you be in? Radians, good. Radians, good. And now we need to find the following. We want to find how many multiples of lambda is A. So we got this relationship between them. So we have solution. We have beta is equal to all that. I want how many multiples of lambda is A, so I want to solve for A divided by lambda. That will tell me how many multiples. If A over lambda is 7, then it's 7. So A over lambda will equal to beta divided by 2 pi sine of theta. So we have 66 over 2 pi and then sine of 7 degrees. But now you have to switch back to degree mode in your calculator, right? Because you're taking sine of 7 degrees. And if you plug it in, you will get a number. Okay.
86.2.
86.2. Yeah. So that number happens to be about 86. So A is about 86 times lambda. Okay. The second example. let's consider the following situation. We have a screen. The screen is a distance L equal to 6 meters. Here's the middle. Here is A. Let's say A is 0.24 millimeters. 0.24. No. This is A. So A is 0.24 millimeters. Let lambda be, for this case, 633 nanometers. Okay, lambda is 633 nanometers. Okay, I think that's all I need. And the question is, what's the intensity at distance 3 millimeters above the center? What's the intensity at distance 3 millimeters above the center, meaning here? Let's say we're here. Distance y equal to 3 millimeters. What's the intensity at that position? Okay. How would we do this? We have the intensity formula.
Find the angle.
Find beta and then plug it in. And okay. So you mean theta or
Theta.
so? Okay. So we will. Yeah, that sounds good. So you're saying do this. Here is we have the following. Beta is equal to 2. Let's do beta over 2. Beta over 2 is equal to pi a over lambda times the sine of theta, right? Pi a over this times the sine of theta. And then the angle is small, right? All of our angles are small. Here's, by the way, here's theta. This is theta. The angle is small, so sine theta is almost equal to tangent theta, and tangent theta is y divided by L. Right? Tangent theta is y over L. So we write this as pi a over lambda and then y over L. And let's plug these numbers and see what we get. So we have pi, a is 0.24 millimeters, so that's 2.4 times 10 to the minus 4 meters. Y is 3 millimeters, so that's 3 times 10 to the minus 3 meters. Over lambda, lambda is 633, that's 6.33 times 10 to the minus 7. L is 6 meters. Okay, 6 meters. 10 to the minus 4 times 10 to the minus 3 is 10 to the minus 7, but we have 10 to the minus 7 on the bottom, so these all go away. And then we have to multiply those. So if you multiply them, you will get beta to be beta over 2 to be about 0.6 radians. Is that true? Let's see if that's true. 2 times 3, that's about 6, and then pi over 6 is about a half. Yeah?
Are you saying sine theta is y over L because the angle's small?
Yeah. Because y over L is tangent, right? And tangent is almost equal to sine for small angles. And you agree it's small, right? The angle, yeah. In this case, by the way, we don't have to use that approximation. We can say tangent theta is y over L, find theta, and then take its sine. But then you will find that you'll get basically the same number. Probably like 3 or 4 sig figs. So beta over 2 happens to be 0.6. Please tell me if I got that right. 0.6 radians, beta over 2. I'm still struggling to figure why that's the case. 6. Pi over 6 is like a half. So what am I missing?
I got 59.55.
59?
I mean, I'm probably wrong, but I got
It would not be 59. Is someone tell me?
Got the same thing.
0.6?
0.59?
Okay.
Yeah.
Oh, yeah. I'm thinking 0.06. Yeah, because you're left with about 3/6. Yeah, okay, that's fine. Yeah. Okay. Somehow okay, sounds good. All right, we're doing okay. Then the intensity is equal to I naught times sine of beta over 2 over beta over 2 squared. So that's sine of 0.6 over 0.6 squared, times I naught. And this will be 0.89 I naught, 0.89 I naught. So that's the intensity in terms of I naught, of the maximum. So it happens to be about almost 90% of the maximum. Okay. Diffraction grading, we talked about it in lab or in discussion. But let's talk about it also briefly and then do a couple of examples on that. So diffraction grading, we said you take a piece of glass or some material and you slice it, you make many slits, right? So you take a piece of glass, let's say it's this long, and then you slice it into many. The line density is the number of cuts you make per centimeter or per meter, per unit of length. That's called line density. So line density is number of lines per unit of length. For example, if it's, let's say we cut 1 centimeter by 1,000, then the number of lines is 1,000 lines per centimeter. Okay, 1,000 lines per centimeter. So for example, let's say the line density example. If the line density is 1,000 lines per centimeter, right? What would the distance be between two slits? What would the distance between any two slits? This is D.
1 over 1,000 centimeters.
Exactly. You took a centimeter and you divided it by 1,000 times. So the distance between any two cuts, any two slits, would be a centimeter over 1,000. So in that case, we get D would be 1 over this. And so it would be 1 centimeter over 1,000. And that means it's just 1 times 10 to the minus 3 centimeters, which is 1 times 10 to the minus 5 meters. Okay? So D would be small. So 1 over the line density gives you D, and 1 over D gives you the line density, right? So they're the reciprocals of one another. Okay. So how does diffraction grading work? So we're going to now exaggerate it. This is already exaggerated. The lines are not that spaced. That's already too far. We're going to exaggerate it even more. So here they are. Make So let's say the distance is d. We went over this, so let's quickly just recall what went on. So here is the screen, and this is L. Distance from here to here is L. Here is the center. Okay. And we said, suppose this spot happens to be constructive interference. Okay? If it's constructive interference, I know, first of all, the distance from here to here, if this is theta, this is going to be d times the sine of theta, right? And we said, okay, let's look at this one here. That distance is going to be twice d sine theta, and this distance is going to be 3 times, right? D sine theta. And I mentioned that if these two have constructive interference, if d sine theta, if they have constructive interference, it means that d sine theta is a multiple of lambda, right? Is a multiple of lambda. If d sine theta is a multiple of lambda, guess what? 2d sine theta is also a multiple of lambda. And 3d sine theta is a multiple of lambda. So they're all multiples of lambda, and they're all constructive interference. So the first slit and the second slit, they interact constructively with each other. And then the rays or the light coming in from the second slit and between the third slit and the first one, constructive interference. The fourth one and the first one is going to be constructive. And then similarly, between the fourth and the third, the distance between them, how much is the distance between the third and fourth? D sine theta, right? So it's still constructive. So it's constructive for all of them. So you see a higher intensity bright spot over there. And the peaks will be really sharp. You get bright, and then you have a gap of dark, and then you get bright, and so on. So an M is equal to 0, plus or minus 1, plus or minus 2, and so on. So it behaves exactly the same way as double slit. Okay, so this is similar to double slit. So that's the diffraction grading. I'll do a couple of examples of that. Suppose we have a diffraction grading. Here it is. Okay. And this is the center. And you send light of lambda 632.8 nanometers. Okay, so we're shining light on it of that wavelength. And the first bright spots occur at plus or minus 17.8 degrees. So let's say here is M1, M equal to 1, and this is M equal to 2. And you do see a bright spot here and here, and these angles are 17.8 degrees. And this one obviously is also 17.8 degrees, plus or minus, so one of them is positive, the other one is below, so negative 17.8 degrees. Okay. The first question is find D and find the line density. So let's ask the first question. Part A, find D and the line density. That's part A. Any ideas on how to go about doing part A? I might need your help with the calculator. I think I do have the numbers, but So how do we find D? Where do we start? D sine theta equal to m lambda, right? Yeah. So that's a good starting point. So that means D. So this is the solution. In this case, m is equal to 1, so that means D will equal to lambda over sine of theta, and that is 6.328 times 10 to the minus 7 divided by the sine of 17.8 degrees. Okay. And that will give us D. If you get D, let me know. In fact, I'm going to keep D in nanometers because I don't really need to convert it to meters. So I'm going to keep it in nanometers. So 6.38, like so. So can we get D in nanometers?
2070.
2070?
Yeah.
Okay. Nanometers. So D is 2070. I tell you how much I have. Yes, 2070. 2070. So how do I get the line density? Let's say I want the line density in centimeters. How many lines per centimeter?
1 over that times.
Yeah. So change D to centimeters and multiply by, and do 1 over, right? So there it is. So D is 2.07 times 10 to the minus 7 times 10 to the minus 6 times 10 to the minus 5, is that true?
Yeah.
Okay. Centimeters. So line density equal to 1 over D. So 1 over that number tells you how many lines we have per centimeter. And per centimeter, if you do it, I have 4,830, right?
Is that to convert to meters?
Is that in centimeters or meters?
Because I got that same number, but I converted to meters.
Oh, okay.
I got 48,309
In
in centimeters.
centimeters.
In meters, you should get more lines per meter than centimeters, right? Because
In meters? It's more
Yeah.
in centimeters.
Oh wait,
That's 2 times 10 to the power minus 6. Oh, no.
no. Okay.
1 over 2.07 times 10 to the negative 5 is 48,389.
1 over this number?
Mm-hmm.
Let's see. Oh,
It should be 4.
this should be to the 4th power?
I think so.
Okay. Let's see. This will be times 10 to the minus 9, so it's 2.07 times 10 to the minus 6. Convert to centimeters. Yeah, 4. Yeah, you're right. Okay. And how about now? Does it work? Okay. And it's line density, so the number of lines should be a whole number, right? So you should round. So 4830 lines per centimeter. Okay, how about the next question? It says, for this example here still, how many additional bright spots beyond, let's say, how many additional bright spots would we see beyond, we know we will see here, here, here. This is m minus equal to m 2 minus 1. Will we see m2 and minus 2, and m3 and minus 3, and then m4 and minus 4? How many more can we see? Right? That's the question. So, what should we do in that case? What determines how many lines we see?
M.
Huh?
I think.
The M, and how do I know where to stop? Which M is where to stop?
You can,
Look at the equation.
The angle?
The angle, yeah. Sine theta can't be more than 1, right? Because let's solve for sine. So you got, for part B here, notice sine theta is equal to m lambda divided by d, right? And can just go on forever because the sine will exceed 1. So it can't be more than 1. Okay? So theta is equal to sine inverse of m lambda over d. And so let's test for m equal to 2. If m equal to 2 works, then m minus 2 also works, right? And so let's see. For m equal to 2, we have theta is equal to sine inverse of 2, right? M is equal to 2. Lambda is 632.8 nanometers, and d is 2070 nanometers. What does this give us? M equal to 2 is, what's the n? Should be more than 17, right?
37.69.
Okay, thank you. 37.69, so let me round to 7, right? 37.7. And so there is positive 2, and therefore there will be negative 2 also. Let's try m equal to 3. Theta will be sine inverse of, what should I plug in now?
3
Yeah, 3 times all that, so 3, 632.8 over 2070. Let's see the angle. You got 66.7%? 0.5? Okay, 0.5 degrees, okay, perfect. And so of course there is 3 and there is minus 3. How about 4? Error. So you can't get it. So 4 doesn't exist. Because this number will exceed 1 at 4. So you can see how many additional ones. You would see 2 and minus 2, and 3 and minus 3, so 4 more, right? 4 additional bright spots. In addition to the ones that I already have on there. Okay, I have one more for the diffraction gradient. It says if a diffraction grating produces third order bright spot for red light, yeah, let me pause it